at the very start of this week, Google announced yet another breakthrough that I find particularly exciting.
Scientific breakthroughs are great for science, but there needs to be at least parts of that translates to something that customers value and ultimately want to pay for.
With a new quantum processor that they call Willow, they really worked to get their errors down in such a way that when they added more qubits into their system, they actually saw the errors decrease.
And everybody claps and yay. And I'm sitting there and I'm like, okay, so what? Does this mean we're now doing things faster, better?
Can you simulate a quantum computer on a classical computer?
So the answer to this might surprise you. And the answer is yes, you actually can.
I paired up with a young quantum scientist. She was finishing up her PhD at the time, and together we just said we want to do something.
Hi everyone, welcome back to The Curious Coconut. Today I have two very lovely guests, Biliana and Danni. They're both in the quantum tech ecosystem. And Danni is a scientist and Biliana has her own not-for-profit organization. Biliana, do you want to quickly introduce yourself to our audience, and then maybe Danni can do the same?
Sure. My name is Biliana. I currently wear two hats. I work at a company called Quantum Brilliance. We're a quantum technology company that use synthetic diamonds, nitrogen vacancy centers in diamonds to build quantum computing systems and other quantum diamond materials. My role there is I lead strategy and I work on corporate communications. And then that's my day job. And then in my spare time, I co-founded with another quantum scientist a nonprofit organization called Quantum Women, where we want to help women who have chosen quantum science and quantum technology as their career to help them thrive in that environment.
Awesome. Hello, everyone. My name is Danielle Holmes, or at least that's my science name, but you can just call me Danni. That's my casual name. And I'm a postdoc researcher at UNSW in Sydney. And my group works on building qubits, or the fundamental building blocks of building a quantum computer in silicon chips. So we really love having silicon as our material because it's the same material that we have in our phones and laptops, so we can leverage all of the information and expertise in this area. And we make our qubits by implanting single atoms into the silicon chip. And we're working to scale up there to build a quantum computer. And I did my PhD also in quantum physics at the University of Melbourne, working on also building a quantum computer in silicon, looking more on the ion implantation side for material science. But I'm a super passionate quantum physicist.
That's great to hear. And what got you guys started first in quantum computing? Like, what was your first sort of foray into this area?
Well, for myself, I got into quantum about 4 years ago. I started working at an organization called Sydney Quantum Academy as their inaugural industry engagement manager. And at the time, they were looking for someone with an industry background to come in and bridge the gap between industry and academia. So for a couple of years, I worked there and I got to know pretty much almost the entire Sydney quantum community from at all levels. And I also got to know the co-founders of Quantum Brilliance during this time. So after a while, I decided that I wanted to go back to industry, and I've been in startups for a few years leading up to that. So wanted to stay in startups, wanted to stay in deep tech, and so I sort of stayed on that field for the past 4 years.
That's great. And what about you, Danni?
For myself, I've known that I wanted to be a physicist from an embarrassingly young age of around 4 years old.
Oh, wow.
And originally, I wanted to be an astrophysicist. And I would go around saying this big word, astrophysics, that I didn't really understand when I was super young. But I was inspired to do this when I saw a comet shooting across the night sky. And I wanted to learn more about the universe as a whole. And then as I progressed in my scientific endeavors, I realized that it was going to be very unlikely that I would get to physically encounter these amazing astrophysical phenomenon. Like, it's probably unlikely that I'm going to get a research project that's going to let me poke a black hole, for example. So I wanted to find something that's a bit more hands-on, something that I can make with my own hands and measure in a laboratory. So that kind of led me down the road of quantum physics, and I became very fascinated with tiny things instead of massive things. So the atoms and electrons that we're all made of. And I was really drawn towards the fact that they obey different laws of physics to the classical physics around us. And I think that quantum computing is the most exciting real world application of quantum physics that we have today. And I'm super excited to see all of the applications that will come out of quantum computers in future. And as a bonus, I get to make and control tiny quantum systems with my own hands in the laboratory. So it's basically the dream job for me.
Yeah, it's great.
Can I just jump in real quick? Actually, this is fascinating. I didn't know this about you, Dan. I've never heard somebody who's wanted to be some sort of physicist at that early age. How did you stay there, as a teenager, 11, 12, 13, how did you stay the course?
I just found it super interesting, like wanting to learn why we're here on this planet, in this solar system, in our galaxy, in this universe, like trying to figure out and make sense of the world around me. I just was always super interested by that, and reading books outside of school and getting exposed to science documentaries like Brian Cox. I used to love watching his documentaries on TV. And I was also a big fan of watching Doctor Who. So I was like, how can I become Doctor Who? So I basically decided if I do a PhD in physics, then I'll become a doctor of physics, which is almost like Doctor Who.
That's great. And yeah, it's funny you mentioned that because as a child, I also wanted to be an astronaut, like for the longest time. And I think I had similar like kind of inspirations as well. Like, I think in grade 6, I started learning a lot about space and planets, and like I was just fascinated by Mars and like, how we can go to these planets, or the world, or like the universe is so vast, and our understanding of it is so like not, I mean, it's getting better and better, but we still don't understand a lot of things. And all of those mysteries just fascinated me. But as I grew older, I was like, it's going to take a lot of effort for me to become an astronaut. Like, I'll have to study for I don't know how many years. And then, even though I really liked physics, I was like, yeah, I don't think I can do that for the rest of my life. So I decided to switch careers a little bit. But it's great that you're still doing it. But yeah, what is quantum tech? Do you want to explain that to our audience?
Yes, so quantum computing, in order to be able to understand the basics of quantum computing, we first have to jump back to think about how our classical computers work. So these are the
Okay,
computers inside our phones and our laptops. And I'll briefly just go through how they work and then talk about the differences with quantum computers.
sure.
So in our classical computers, we basically store and process information in bits, which are the zeros or the ones. And we make these bits out of transistors, which are basically teeny tiny switches in a silicon chip that are either on or off. And these are the 0 or the 1 states in the bits of information. And in a classical computer, these bits of information are strictly 0 or 1. There's no in between. It's not like a mixture of on and off for the transistor. It's either on or off and nothing else. And we basically use our classical computers by feeding in these bits of information in a string of zeros and ones, and then we run some algorithm on these bits, and this switches the zeros and ones of various bits, and then it spits out the answer in the form of a string of bits as well, and then we can read our answer. And for the quantum computers, on the other hand, instead of the classical bits of information, which are 0 or 1, we store the information in quantum bits, which are also more fashionably known as qubits. And in order to build a single qubit, all you need is a quantum system that has at least 2 energy levels that can be used as the 0 and the 1. And because these are quantum systems, they have the very interesting property of being able to be 0 and 1 at the same time in a superposition. So this is the main difference with quantum bits versus the classical bits in our classical computers. And there's many different ways to build these qubits. You can use photons of light, you can use electrons, you can use atoms, you can use superconductors, and the jury's out as to which way is the best way to build a qubit. But one of the textbook examples is using an electron spin in a magnetic field that either points up or down. And this is the qubit that we use at UNSW in my research group in silicon. And basically, we are looking to scale up to having multiple qubits in a silicon chip that we can entangle multiple qubits together so that they share a quantum state across many qubits. And then instead of a classical computer, which increases its processing power linearly, so basically you add bits and it increases the processing power linearly, with a quantum computer, when you add an extra single qubit and entangle it to the existing qubits, it increases the processing power by double. So it's an exponential growth. So we've got exponential increase in the processing power of a quantum computer instead of the linear for classical computers. And this is what's really exciting with being able to solve more complex and exciting problems that we're currently unable to do with our classical technology by having quantum algorithms that can operate on these qubits in fewer steps than would be required for a classical computer.
Wow, that's a lot of information, and I have a couple of questions I want to ask just so I better understand. So you mentioned there needs to be like two energy levels for the electron. So I'm assuming this is the spin up or spin down, right?
Exactly. So for our 0 and 1 in our qubit, we encode that as a spin up or a spin down of the electron that lives inside the silicon.
And then how, like the concept I don't understand is how are they both like in both of those positions at the same time? Like how does that work? And I just can never wrap my head around it.
Well, it's very fair that you can't wrap your head around it because we don't have a classical analogy. So this doesn't happen in our classical world.
Yeah.
Everything is either one state or the other. It's nothing in between. But there's the famous Schrodinger's cat paradox, which kind of highlights how different quantum physics is to the classical world, where basically you've got a cat in a box, and this box contains a radioactive source. And if this atom, which is a quantum particle, if it decays, then there's going to be poison released into the box and the cat will die. But because the atom is a quantum particle, it's in a superposition of having decayed and not yet decayed at the same time. And this basically means the poison is in a superposition of having been spilt and not spilt at the same time, and therefore is the cat like dead and alive at the same time. And this is like the big paradox because we don't ever think of it being possible of a classical animal being dead and alive at the same time. And it actually wouldn't be because of all of the decoherence effects taking place. But on the quantum scale, at the level of atoms and electrons, these quantum particles can be two states at the same time. So like, for example, with the electron, it's literally a spin up and a spin down at the same time if it's in a superposition.
Is it something along the lines that as long as you don't measure it, it doesn't lock in? Like once you measure it, then it remains in that particular position, like spin up or spin down? Okay.
Yes, exactly. So with the quantum computer, when you're running the algorithm, the qubits are in a superposition of being 0 and 1 at the same time, and they're all entangled with each other. But once you spit out the answer of your quantum calculation, that gives you a string of qubits, and then when you measure them, that projects the answers into 0 or 1 for each of the qubits. So once you measure it, it's either like a spin up or a spin down. So the act of measurement fundamentally changes the quantum system.
Okay, so the qubit doesn't actually take a state until the answer has been calculated. Is that correct?
Once you measure the qubit, it's definitely either a 0 or a 1.
Yeah.
But before you measure the qubit, it's like a probability distribution.
Okay.
So it's more like described by this cloud of probability, also known as a wave function. And so it's only once you measure this wave function that it collapses to a certain state, 0 or 1.
Yeah, that kind of makes sense. And the other thing I want to ask is, what is quantum entanglement? How does that work?
Quantum entanglement is where you can't describe a single quantum particle by itself if it's entangled to another quantum particle. So if you have two quantum particles that are entangled together, it no longer makes sense to describe one particle by itself in a particular state, because it fundamentally relies on what the state of the other particle is doing at the same time. So for example, you could prepare some photons of light, and if you say that one of them is a spin up and the other one is a spin down, for example, then the only knowledge that we have about the system is that the photons have opposite states, but we don't know which one is an up or a down until we measure it. So you could take these photons to the opposite sides of the universe, and as soon as you measure one of them, if you measure that to be up, for example, then the other one is down instantaneously.
Yeah. Okay.
So this is what Einstein called the spooky action at a distance.
Yeah, I think I heard that before. And then how does quantum entanglement, like, does it make the quantum computer faster?
Exactly. So in order to have a quantum advantage where the quantum computer can perform simulations or solve problems faster than a classical computer can, then you need to be able to entangle your qubits together. So when you add an extra qubit into this already entangled system, then that's where you get the exponential growth of the processing power. But it relies on the principles of superposition, where the qubits can be in 0 and 1 at the same time, and also the principle of entanglement, where each qubit relies on the states of other qubits in this quantum computer.
Okay, and then one last question. How do you actually entangle two particles together in a quantum state?
There are many different ways to do that. And for example, one way that we use in our research at UNSW is we can entangle the spin of a single nucleus in an atom implanted in silicon with the spin of an electron through something known as the hyperfine coupling. So it's basically how the magnetic field of the electron influences the magnetic field of the nucleus. And so the spins become entangled. But there's many different ways to do it. You can also do it with photons, where you could basically conserve momentum. And this says that each photon has to have, for example, the opposite spin. Many different ways to entangle particles together.
I'll be honest, I don't think I fully understand that, but I think I'll have to study, get a PhD in physics to actually do it. But I think, yeah, that makes a good sense, good amount of sense, I would say. Coming back to quantum computers, where is this technology currently at?
Yes, so in order to have a useful quantum computer that will solve problems that will be useful for our day-to-day lives and to advance upon what we can already do with our classical computers, we're going to need an extremely large number of these qubits, or the fundamental building blocks of the quantum computers. And it's estimated we're going to need millions or even billions of these qubits to make the quantum computers perform useful operations. And at the moment, we're definitely not there yet. So there is currently no useful quantum computer in the world yet, because we're still on the order of tens to just about breaking into the thousands of qubits. So we've still got a long way to go to reach those millions and billions of qubits that we'll need to make a quantum computer work. But it's not just the size that matters, it's also the quality of the qubits. So it's not just a case of blindly adding more and more qubits to your quantum computer to make it bigger and faster and better. You also need to worry about the quality of the qubit. And because the quantum systems are very sensitive to noise, they're subject to a lot of errors. And you don't want these errors to build up when you're performing these quantum calculations on your quantum computer. So you have to get really low noise and isolate your qubits from the environment as much as possible so that they're not sensitive to noise and they're not going to be subject to errors that will cause your quantum computer to not work properly. So we also have to work to get higher quality qubits.
Okay.
And I think if I add to that, Danny said, you're going to need millions and billions of qubits. And there's a school, obviously, that thinks and believes and builds systems to that. But what we do at Quantum Brilliance actually is we believe in massively parallelized systems, where we're basically saying you don't need a million or a billion qubits. We're working on miniaturizing our systems so that they can actually just, you can place, I don't know, 10, 100, 200 of them next to each other. And we're working on figuring out how they can then talk to each other in a way that 1+1 = 3, so to speak, or how do we get them to jointly work together with less qubits, but many, many more of them.
Okay, that's interesting. I think my next question is, because you mentioned earlier that you're creating these in silicon chips, right? How do you isolate the silicon chip so it's has the highest performance?
This is a great question. So in our research, we use a silicon chip as the substrate in which our qubit lives. And then we can have this electron spin that's either a spin up or a spin down in a magnetic field that's our 0 or our 1 for our qubit that I mentioned previously. We can isolate that in the silicon by implanting a single atom of phosphorus, for example, and then it binds an extra electron to this atom just by the positive charge that it has in its nucleus. So that's how we isolate the electron in the silicon chip to make a qubit. But now we need to isolate the qubit from the noise in its environment so that it can perform as well as possible with really high fidelity operations. And the way that we do that is by isotopically enriching the silicon. So if you have natural silicon, it has 3 different isotopes. And one of these isotopes is really bad because it has a spin in its nucleus. So this is like flipping spins around our qubit that we want to protect from any noise in the environment, and that would be bad. So we have to isotopically enrich the silicon so that we can get rid of all of these spins in the nuclei of the isotopes that we don't want. So we use this very high purity isotopically enriched silicon-28, which acts as a semiconductor vacuum. So it's almost as good as having your electron just isolated in free space with absolutely nothing around it. It's in this perfect silicon crystal lattice with no spins in its environment. And we also have to put it in a dilution refrigerator to get it down to very low temperatures to minimize the noise that acts on it and be able to measure tiny signals from our quantum system. So we use this big, powerful refrigerator that can get down to close to absolute 0 temperature. So it's 100 times colder than outer space. It's colder than any known place in the universe. And we need these really low temperatures to be able to operate our qubits with the highest performance.
Oh wow, I didn't think that you required that kind of temperatures for the computer to work.
Well, I'll tell you, at Quantum Brilliance, our whole thing is room temperature. Because
Oh,
we're
okay.
using, yes, so this is why this entire field is fascinating, because there are various different modalities that are currently being developed.
Yeah.
And the consensus, at least from what I've seen, is there isn't going to be a winner, but there will be winners. And there will be certain things that are more applicable, certain modalities that are applicable to certain cases or certain situations. Because we use synthetic diamonds, and the way our guys sort of process and creates the qubits and encase them and basically create a room temperature chip, our systems should be, or the mission is to basically put them on in a car, or in, let's say, your laptop, for example, or in a data center, or different mobile devices, because of the material that we use. So we don't cool it down to these temperatures.
Yeah.
So it's really fascinating following knowing all of us who are working on so many different things.
I completely agree with Biliana there. It's such a fascinating time to work in the field of quantum computing because at the moment there's no clear winner, and each qubit platform has its own pros and cons, and we're just working to push our particular platform as far forwards as possible and see where that goes. It's kind of like the modern day space race, I think.
Yeah, definitely. I think it's a very interesting space because there isn't a clear solution yet. So all the solutions that people that are researching are all kind of correct. And then you just have to find the right one, and there can be multiple right answers here. So there's nothing really like holding you down. My next question is, I think you kind of touched on this earlier, but what are the major challenges that are kind of um, coming in this industry, or like that are hard to overcome at the moment?
Yes. So the major challenge for quantum computers is that these qubits are extremely fragile. So they're very sensitive to the noise in their environment, as I mentioned previously. And so depending on which system you're using, you have to find ways to isolate it from its environment, whether that's the isotopic enrichment of silicon or extremely low temperatures. So that adds to the technological challenge of building your quantum computer to be able to make the error rates as low as possible in the qubits. That's going to be a big step that we're working towards to solve. And also there's, for example, in my field with the silicon chips, it's going to be a fun engineering challenge to fit many millions of qubits onto a silicon chip that lives inside this dilution refrigerator that can be at super low temperatures. So you've got all of like the cabling requirements, and we want to make sure that we're not heating up our chip too much so that it no longer has nice quantum properties. So we have to think about heat dissipation, cabling, spacing. And another issue, I think, as we're scaling up to larger numbers of qubits, is how can we be sure that we're controlling a particular qubit that we want at a particular time without having crosstalk. So just like focusing on controlling just a single qubit within an array of qubits, it might have some other influences on neighboring qubits around it. So we have to be able to do single qubit operations on particular qubits when we want to, but we also have to be able to controllably entangle certain qubits with each other when we want to as well. So that's the big fun science engineering challenge there that's going to need many different researchers in many different fields to solve.
Yeah.
And I think also challenges, non-scientific challenges, is for those quantum startups that are out there, is actually getting industry on board on this, because this isn't a system that once ready, you're just going to be plug and play. There's a lot of collaboration involved. Like, for example, we're working with a customer to try and understand how the quantum system integrates into their classical infrastructure. And that's something that the other side actually has to devote human capital to, devote a budget to. And so sort of from where I sit is basically getting industry involved in this. And it's hard for industry to try and set budgets aside for something that may or may not work. How do you explain to your boss, can I have $3 million to explore this? Well, what's the value we're going to get? Unclear. So it's actually, that's also what I see from, with my commercial hat, is actually getting companies, non-quantum companies, to work with us and collaborate with us, because we need that input. We need to make sure that what we're doing and how we're thinking actually makes a difference in the real world. Calculations that we're doing or scientific discoveries that are being made, do they actually matter to a company? And it's that sort of dialogue that I personally wish would happen more. It's certainly happening more than it did 3-4 years ago, but I'd just like to see much more of it.
Yeah, so there's both the technical challenges as well as the industry challenges. It's like how companies will be adopting this technology in the future, but also the funding and use cases of it. So I guess there's a lot to work through. Next question I have is, have there been any major breakthroughs in this industry so far?
Yes, so there's many breakthroughs happening all the time with many different heavyweight companies competing around the world to increase the numbers of qubits and also increase the quality of each qubit, so reducing the error rates as much as possible on my qubits. And also many university research groups doing the same on a smaller scale, looking at particular qubit platforms. So in 2019, there was a really exciting breakthrough which for the first time showed a quantum advantage. So this is basically the case when Google in 2019 was able to demonstrate for the first time that a quantum computer could solve a very niche, very particular problem faster than it could be solved on the world's largest, most powerful classical supercomputer at that time. So even though this problem didn't have any real uses in our everyday life, it's a demonstration of the potential power in future for quantum computers to be able to leverage the superposition and entanglement to be able to solve particular problems faster than classical computers. And as this industry progresses and we get more qubits with lower errors, then we're going to see the numbers of problems that quantum computers can solve faster than our regular computers exploding. And we don't know in which way that's going to go in future, but there's so many exciting potential applications that can come from that. And we were mentioning just offline before we started this podcast that there's been a really big breakthrough just this week alone.
Yeah.
So at the very start of this week, Google announced yet another breakthrough that I find particularly exciting. So they weren't so much concentrating on the numbers of their qubits, but they were looking more into the quality of their qubits. So for the first time, with a new quantum processor that they call Willow, which has only 105 qubits, so it's a relatively modest number of qubits, but they really worked to get their errors down in such a way that when they added more qubits into their system, they actually saw the errors decrease. So this is the first time this has happened, where adding more qubits reduces your error instead of creating more issues and more errors. So this was a really nice breakthrough from this week.
So, like, there are already functional quantum computers out there?
So no, there is no functional quantum computer in the world in terms of it being able to solve a problem that is actually useful for humanity.
Oh,
So
okay.
at the moment, we only have on the order of tens to thousands of qubits, which are really useful as a test bed to demonstrate quantum algorithms on a small scale and to be able to demonstrate very niche particular problems that don't really have any use that we can run faster than our classical computers. But we don't have a fully useful universal quantum computer that can solve problems yet. We'll need more years of research and many more billions of dollars of funding to be able to get to the millions of qubits with low error rates needed to be able to solve useful problems.
Okay. And then I just had a random thought. Like, can you simulate a quantum computer on a classical computer? Like, is that possible?
So the answer to this might surprise you. And the answer is yes, you actually can simulate a quantum computer with a classical computer. So you might be wondering, well, what's the point in a quantum computer then if you can just simulate any problem that you could solve on a quantum computer with a classical computer? And the answer is that it's very incredibly inefficient to be able to do this. So for maybe a handful of qubits, you could simulate that with a classical computer just by extreme number crunching. But as you get to larger numbers of qubits, for example, 50 and above, there's going to be quantum algorithms that could operate on those qubits much quicker than you'd be able to simulate them on a classical computer, just by the amount of resources that you need to have to simulate with a classical computer is going to increase exponentially as you're adding the qubits. And so even though it's really useful at the moment to be able to simulate small numbers of qubits on classical computers, basically just to check that the answers that the quantum computers are spitting out are correct, and to be able to develop some basic quantum algorithms, then in future, we're going to see quantum computers overtaking the classical computers, and we will no longer be able to simulate what we can do with the quantum computer in a reasonable time that doesn't take, for example, the age of the universe.
Okay. Well, yeah, I think there's definitely exciting times ahead. I want to switch it up a little bit and Biliana, talk to you a bit more. So you're into startups. What led you onto the startup journey that you're currently on?
Well, I think one's career has elements of planning, and other times things just sort of happen by circumstance or by luck. I started my career in technology in the mid 90s in New York at, I think, what could arguably be called startup. It wasn't venture backed, but we were about 50, 60 people, and we were developing enterprise software.
Okay.
And so I worked as a product manager, customer success manager, sales, like I did everything but the programming. And we also we had a couple of products, and then we launched a new one, and that I was in charge of, and we were serving the financial services industry. But at that time, I didn't fully appreciate technology. This was the mid to late 90s, the heydays of investment banking. It was the economy in America was going great. And so I wanted to do investment banking. And so for about 12 or so years, I then moved into doing investment banking. And it's almost 7 years ago, I sort of made full circle back into tech. For me, it happened to be a client of mine who knew somebody who was starting a company
Yeah.
and thought that it might be something where my skill set and my background could be helpful. And so I joined a company doing AI. They were doing AI speech analytics. They've taken NLP research out of Deakin University and turned it into a product for call centers. And I joined right after our seed round and stayed there for about 2 or so years, and then had my hand in participating in the Antler incubator program for a few months. I think COVID hit. This new role at Sydney Quantum Academy sort of came up through a friend actually who had popped up in her LinkedIn as a job for her, and she's like, no, this is not a job for me, but I think I know somebody
That's
who could
great.
be suitable for this. So that's sort of, I started in startups, so to speak. I then went into big industry and then back into startups. But what I think my time in industry or that sort of corporate helped me with was it was a very structured environment. It was sort of, here's the strategy, here's what we're going to do, then we're going to execute. And I think that has helped me. That background has been very useful in startups where sometimes things are chaotic or running in 5 different directions. And so knowing how to, all right, here's our problems, here's how we're going to break it down, here's how we're going to, this is the journey we're going to start going on. Like that's, surprisingly, that background actually has been very useful to me, and also perhaps that's also why I enjoy working in startups, because I never, I don't get too stressed. There's always a way. You just have to sit down and have a think about it. That's sort of how I see it. But yeah, that's sort of been my startup journey. It's hard to leave startups if you're actually enjoying it, because it does give you a certain level of freedom. You see impact of your decisions and your actions, and you're really at the forefront of innovation. I've always liked deep tech, and I just feel like we're just coming up and we're talking about things that only years from now will be adopted into
Yeah.
corporations. So I just find it very exciting.
Yeah, it's definitely more exciting to work in a startup because I think in corporate things can take really long to get through or to actually see the impact of. Whereas with startups, you know what you're doing, and if you're not doing it correctly, then you're going to be out of business very quickly. So it's definitely more motivating. You also have your own, not a startup, but an organization that you started, Quantum Women. Do you want to talk a bit about that and what they do there?
Yeah, that's sort of a personal passion of mine. Having spent my career in investment banking, that it's a very male dominated area, and I once I started working in quantum, I saw how it was even more male dominated,
Oh wow.
and yeah, and it's I've never been the only woman in a room,
Mm-hmm.
um, but I see in quantum often are, or maybe the only woman in a research team. And so that must be very challenging. And so I paired up with a young quantum scientist. She was finishing up her PhD at the time, and together we just said we want to do something. We want to, we what do we do? We want to do something. And so we created this professional network where we want to make sure that the people who are the women who are self-selected into this area sort of have the stamina and persistence, like stay in there, because there will be challenging times.
Yeah.
And so we also want to elevate their voices and enhance their profiles to make sure that they are given opportunities, they're given the confidence, or they're given the opportunities to sort of persist through challenging periods, whatever that might be. And so one of the things that we do is we every 2 weeks we spotlight someone. It's our research spotlight, where if there's a female author or a co-author of a scientific paper, we talk about that research.
Okay.
And another thing we do is we've created a series that we call Under the Hood, where it's both for quantums and non-quantums, but it's basically to find a way to virtually connect research institutes and companies who are looking, quantum companies with potential future female employees. And so we organize sessions where people talk about their career journeys, so that people who are listening can interact with them and also kind of see from a cultural perspective, is this the company I want to work with? Is this a research institute where I think I'd be happy, etc. So that's sort of a couple of things that we do, and we also try and organize in-person events. We all do it on a volunteer basis, so I don't think we're doing enough, but we're one by one chugging away there, I guess.
Yeah. I think even like doing on a voluntary basis and just having that community where women can come together and talk about the challenges they face, or just connecting them with other, people who can help them. I think that's just really great. Even though, it might be a bit stressful at times and you feel like you're not doing enough. But even the fact that you started it and you're here, so I think it's a big accomplishment in itself.
Yeah, I mean, you mentioned something, talking, hearing and talking about challenges. That's something that we have found people want to hear stories, and it doesn't necessarily have to be challenging stories, but I think there's a certain level of comfort, if you're struggling, or I don't want to say struggling, that's not the right word, but if you find yourself challenged at work, to hear that other people that have gone before you, they have faced challenges, and
Yeah.
yet here they are, and here you consider them a role model.
Yeah.
So it's not about the challenge itself, but it's okay, everything that I'm going through, we can overcome this, even though sometimes it doesn't feel like that. So
Yeah.
it's definitely like hearing other people's stories and hearing other people's lives that provides that motivation for others.
Yeah. Yeah, it just gives them that feeling that you're not the only one who's experienced this. And,
Yeah.
if other people have made it work, that gives you courage to do it yourself as well. What would you say are the major challenges that women face in the quantum industry and I guess STEM overall?
Uh, I think I'll have Danny, chime in whenever you feel. I think to me, it's how do I verbalize this?
Yeah.
I don't know. Danny, you go first. I'm trying to gather my thoughts here because there's so much that just comes into my
Yeah.
mind.
Yeah, that's okay. Take your
Yeah,
time.
I'd say the main challenge for me when it comes to being one of the small percentage of women in my career in quantum computing is that sometimes it can be pretty startlingly obvious that you are this small minority of people in a particular space. So, for example, if you attend a research conference and then you're just met with a sea of men, you're like, okay, wow, it's quite affronting, and it can increased like imposter syndrome, I feel.
Mm-hmm.
So if you're met with a lot of big, confident, loud personalities and then they're like speaking over you at conferences, it can be very daunting to really try and get your ideas and thoughts across. But I really try and make a point whenever I'm at a conference, I'll at least try and ask one question during this conference so that other women in the audience will also feel confident and comfortable to try and ask questions and get their voices heard.
Mm-hmm.
And yeah, just trying to overcome the imposter syndrome really is the main challenge for me. But I think you can also use it to your advantage in finding extra inspiration to become a role model for other people. So trying to do as much scientific outreach as possible is something that I'm really passionate about. And the more outrageous, the better, to get more visibility, just to show your face in this space, to try and encourage others that it's a very wonderful career and very exciting time to be in this field, and trying to get as many people from as many different diverse backgrounds joining this field is only going to increase the innovations that will come in this space by having different people's perspectives on the matter. And we've got so many engineering challenges to solve to be able to build this amazing technology that we really just don't want anyone to be missing out just by feeling like they don't belong in this space.
Yeah, for sure.
I think when I was younger, I think you do hit the nail on the head on I feel men are more outspoken, and they are not afraid to speak, even though they're not necessarily saying something new. And oftentimes when I was younger, I would think of something and I'm like, well, that's nothing special, and then somebody would just say it and I'd be like, well, that's just so obvious, like you actually didn't add anything to the conversation. And so I do think that women should try and speak up more for themselves, and also promote themselves, and not be afraid to share their opinions, because they're just as good as opinions, if not better, than the next person. So it is definitely something I do think women would do a little bit more. I'm guilty of it when I was younger, not anymore though, but back then for sure.
Yeah, I think especially when you're younger or when you're just starting out, it's harder to feel confident because you just don't feel like you're good enough or you're adding anything. But I think, yeah, just sharing your opinion, even if it's rephrasing something that's already been mentioned in a different way, might help someone else understand it better. Um, so yeah,
That's a very
definitely.
good point, actually. Yeah.
Yeah. Yeah, like that's what I often do as well, because especially with a topic like this where it's super complicated. So someone might say something really complicated, and I'll just repeat the same thing but in a different way, so that I can understand it better just by talking about it. But also it gives a chance for someone else who's listening to me also understand it. So yeah, you can use that in the future.
Yeah, I
Yeah.
think also people should, women should say yes more to opportunities when
Hmm.
they present themselves, and not think about it too much. I'll share my story. About 4 years ago, when I was still at Sydney Quantum, I was asked to be on a quantum panel. That was my first quantum panel. And it
Hmm.
was me and 5 senior men, quantum experts
Yeah.
in the community, all PhD holders, and they had
Hmm.
many years of experience. And so I felt nervous. And also, by the way, I wasn't their first choice, and there's nothing wrong. That's something I tell women. Doesn't matter how you got there. We have to get over this. I was chosen just because I was a woman. There was another woman, but she couldn't make it in my case, so that they next started going down the list, I guess. But it was very intimidating, and it was very nerve-wracking, but I got through it. And then I said yes to another one. And then I said yes to another one. And now I've sat with some of the other people in other panels, and I don't feel nervous and I don't feel intimidated. So I do think women should just say yes and then figure it out, rather than overthink it first.
Yeah. And I agree, like having a diverse panel is definitely more interesting. Like, it because if they're all senior men, the topics they're going to talk about or the ideas they'll have will be very similar to each other. But if you have like a younger person or a woman in your case, in that panel, I think you can add a whole new, or you can bring a whole new perspective to the conversation, which probably would not have happened if you weren't there. So think of it that way as well.
One thing on this topic that I wish would happen in future is that when we're trying to increase gender quotas on panels, for example, typically the choice is so small for the females that they'll have to go for quite a junior research member to be on a panel. And I just wish that they could also have a similarly junior male on the panel as well, just so that it's not
Yeah,
like a row of really distinguished male professors and then one poor PhD female
yeah,
student that has to try and compete there, because
yeah,
it just kind of enhances this
yeah,
potential bias. I think it would be really nice if we could get just get an inexperienced male on a panel one time, you know?
yeah, yeah. As a non-technical person, Biliana, like have you ever found it hard because you're working in deep tech to understand all these concepts that people might be talking about?
For sure. For sure. I don't have a scientific degree. I have a business degree. Um, when I first started, it was definitely a steep learning curve for me, and things that I read, I had to read 2 or 3 times again, and with each time, I understood something more. I personally read a lot of consultant reports because at least they write about quantum in a way using words that I understand, and explaining concepts in the way that I understand. So that's sort of how I've started to get up the curve. Nowadays with ChatGPT, I'd put a research paper up and I said, explain it to me as I typically use this, explain this to me as if I were a sophomore, junior in college. Because I don't want to be explained to as a 10-year-old, but I also, if they try, if it tries to explain it as an adult, I might miss things. So that's sort of my level. And so I pick up on things like that. But the thing is, I'm never going to understand the science and the engineering aspect of things the way scientists do. Just the same, they're never going to understand. They're never going to be as good at what I do.
Yeah.
And my role is really to understand enough to be able to then ideate and tease out possible commercial opportunities as well as problem solve, and then know enough that I can be on the front line talking about what we do, but then bring in the right subject matter experts where suitable. And then I think my role is also internally to challenge our scientists internally. And by that, I mean, on our regular meetings, people might present some breakthroughs that we've done internally, and everybody claps and yay. And I'm sitting there and I'm like, okay, so what? Does this mean we're now doing things faster? Better? Like I challenge them to also to try and reframe that, because I then need to understand, how can this translate to value to customers? And I think when you're working, at a startup, you always have to have the customer in mind, and scientific breakthroughs are great for science, but there needs to be at least parts of that that translates to something that customers value and ultimately want to pay for.
Yeah. Like you're the bridge between the scientists and the people who will actually end up using the product. And it's great that you understand like both aspects of it.
And I think it's super important for the scientific community to try and use language that isn't alienating unnecessarily, because we need to have as many people working in different fields that we connect with if we're going to be able to expand this industry as much as we want to do. So it's also on us to use less technical language where possible. And it's also not an easy subject. Like there's days when, most days I'm learning something new. It's that kind of field where not everything is obvious, and there's going to be things that you didn't know that you can go and learn about. So it's definitely
and also I think it's hard for if you're a scientist with many years of experience, you've sort of reached a certain level, and even if you try to explain it, I don't think you can ever go down to that basic level, because you're so far beyond that even if you want to try and be basic, your new basic normal is different than it was when you were a PhD candidate versus, a professor.
Yeah. Yeah, no, that all totally makes sense. One last question for this part of the podcast. Do you have any advice for any women who, might be trying to get into quantum computing or STEM in general?
I'd say Danni. I mean, she's been wanting it since 4, so.
Yeah, my advice would be just to go for it, because it's the most exciting field that I can think of to be working in right now. And you can really use the fact that you're a woman in this space to your advantage. Like you probably will get offered more opportunities in media or applying for awards because of the fact you're female, and don't be put off by thinking that it's just because I'm a female I'm not going to apply. I think you should just really go for it and use that to your advantage, because we really need to boost the visibility of females in this space to get more females to apply to work in this space. And if you're inspiring others, then that is great. So really just go for it and say yes to the scientific outreach opportunities where possible.
And I think think somebody told me a few years back, think about your career in decades as opposed to the next 12 or 24 months. And I think if you think of it that way, that allows you time to learn something if you don't understand it right away. And especially something like quantum, it'll take you years, you know? And so, don't stress about it. If you think about, okay, this is what I want to devote my next 10 years to, you don't have to, you can, jump off after 5 years, but don't feel that you need to know everything about everything within a couple of years, because then you might be disappointed, unfairly disappointed at yourself.
This is
Yeah.
a very great point, because nobody is born with the knowledge. Everyone has to start from somewhere and learn. So yeah, just don't be put off by the knowledge learning curve, because you can learn on the job. And as I get older in my career, I realize quite a lot of people just fake it till they make it at the start of their careers, and then they just learn on the job, and that's the best way to learn.
Yeah. And I'll have something to add to that. Like when I first started the podcast, I had a very similar experience. I was like, oh, I don't know how I'm going to talk to people. I don't know how I'm going to edit the video. I don't know how to do marketing. I don't know any of that. How would I do anything? But my co-host and I, we just decided, we'll start it. We'll record one episode. We'll post it and see how it goes. And then, yeah, like that first episode probably wasn't the best one, but the iteration we did, we constantly tried to improve with each episode. We learned video editing, we learned marketing, we learned how to manage Instagram, and all those things. Like if you're really passionate about what you do, you'll find time to learn. And so yeah, don't be afraid by if you don't know something. Another advice I would also give is join Quantum Woman, because I'm sure if you're trying to get into STEM, that's a great community that you can leverage to your advantage. Anyway, let's move on to another part of the
Sorry, 1 second.
podcast.
Do you mind if I just do a dance to get the light back on? Okay, we're good. Just crop that bit out. All
That's
right.
all good. Yeah.
I thought you were saying, do you mind if I just do a dance? I'm like, oh, what has she prepared?
Yeah, like I don't know, like if I said something that made you want to dance.
I got my dance out of me. Okay, we're good.
Okay, I want to talk about some applications of this technology. Um, what are the major applications you see for quantum computing going forward, and what are some key industries that this tech can enhance or like change come in the next few years?
Yeah, so I think what I'm most excited about for quantum computers in the future is to be able to simulate molecules and chemical reactions. So the fundamental building blocks of molecules, they're made of atoms with covalent bonds, they've got electrons whizzing around in there. So these are quantum systems. So if we want to be able to simulate them efficiently, we're going to need a quantum computer to be able to do that. So I think we can learn a lot from using quantum computers to simulate these molecules. And for example, we could design new drugs. So that would have huge applications in the pharmaceutical industry. So we could imagine getting really fast turnaround vaccine developments when if a new virus comes out, we could use a quantum computer to do that. And on the chemical reaction side of things, we could look to making our own really efficient catalysts to speed up chemical reactions if we can learn how those take place. So we could get inspiration from biology with the enzymes to speed up chemical reactions, and to be able to make our own catalysts to speed up reactions. And one huge example of that would be to be able to make fertilizers for food. So
Mm,
at the moment, we take nitrogen from the atmosphere, and we use a very intensive process with lots of heat and lots of energy to be able to convert it into ammonia that we can use in soil to provide nutrients for food, crops to grow. And this is so energy intensive, but if we could use inspiration from biology with enzymes that can just operate at room temperature, and they can convert nitrogen from the atmosphere in a very ambient environment and convert it into nitrogen in the form of ammonia that can go into the soil for crops to consume, then we would really help solve the hunger crisis in the world, and it would be a really huge impact on the food industry. So that's just one really cool example that I always like to mention. And there's many other areas that quantum computers will be able to help develop. So for example, with optimizing So optimization problems, quantum computers will be really fast at solving these problems. And this has huge applications in finance, transport and logistics sectors, and also forecasting. So we're all looking to have better weather forecasts so we know what to do tomorrow, whether we're going to go to the beach or not. We're not entirely sure if the weather forecast is going to be accurate, but
Yeah,
hopefully quantum computers, yeah.
I would really like Melbourne weather to be better forecasted because it changes
Yeah.
like 10 times a day. But yeah, keep going.
4 seasons in one day for sure in Melbourne. So
Yep.
quantum computers will be really good at having large data sets and solving really complex problems. So that
Yeah.
kind of area and space. And another really exciting thing would be when it's simulating molecules and it can develop new materials. For example, we could create a new material that could capture a lot of carbon from the atmosphere and contribute to solving global warming. So there's huge applications. And it's going to be the case with our classical computers, where at the very start of the journey in the technology, we didn't know what we were going to be able to use them for. But now we use them for so many different things that I think we have to build the quantum computer first to be able to know what we can do with it later. So really, it's an open book.
Yeah. It's really interesting that you want to use quantum computers to simulate nature itself, and then kind of build it from there and see what we can do from there. Because yeah, I think there's a lot of things we haven't discovered, and we can just use that to sort of fast track that process.
Yeah. Another super exciting example of simulating nature would be if we can simulate the process of nuclear fusion. So where you're bringing two atoms together and fusing it into a different element, then we can learn how to better design nuclear fusion reactors. And this could potentially give us an unlimited clean source of energy. So there's really like big picture ideas that quantum computers could help to solve.
Yeah, those are all good. But what are the negative impacts it can have? Because I heard a lot online that it can easily, break through our current cybersecurity protocols and the RSA that we have set up for like our passwords and encryption and everything.
Yeah. So with RSA cryptography, this is what all of our communication is based off to make it secure. It relies on the fact that it's really hard to computationally factorize a large number into its prime factors. And so if we have a quantum computer, there's an algorithm called Shor's algorithm. That's one of the main algorithms that quantum physicists like to talk about as one really concrete example of where quantum computers will be able to have an impact in the world. And that's that quantum computers will be really efficient at factorizing large numbers, much more efficient than classical computers. So there is definitely the concern that in future quantum computers will be able to crack the RSA cryptography by factorizing these large numbers really rapidly. And I think this is a very real threat. And people like Apple, for example, are looking at ways to make their current data transfer quantum secure already. But I think you don't need to worry too much about this, honestly, because luckily there's a field called quantum communication, which is actually developing more rapidly than quantum computation. And so quantum communication is going to provide us with an absolute 100% secure way of transferring information that is fundamentally secure by the laws of physics. So it relies upon the fact that when you measure a qubit, it fundamentally changes the system. So you can tell if people have been eavesdropping on your password that you're trying to share. So you'd be able to know with 100% certainty if your password that you've transferred to someone else is secure, and then you can use that to encrypt and decrypt your information. So I think this is really promising, and quantum communication will save the day.
Yeah, that's super interesting. Because I think I learned about this in university. There's like a man in the middle attack or something where they get the information and then send the copy of the information to the actual server. So you think that no one has intercepted it, but if you can somehow do it with quantum computing, I guess if it has already been measured, you already know that someone has looked at it. So I
Exactly.
guess that's a very interesting application that I hadn't thought of. Um, But how will this impact AI? Because there's a lot of hype around AI at the moment. And can we use quantum computers to train like AI models and things like that?
So quantum computers will be really good at handling large data sets and solving complex optimization problems that can increase the strength of machine learning models. And quantum computers are also really good at solving simultaneous equations in parallel, which is kind of a fundamental aspect of these machine learning models. So I definitely think quantum computers will speed up the development of artificial intelligence in the future. But I also think that it's already developing so rapidly with just classical computers alone that we really need to be thinking about putting laws in place to make sure that we've got fail-safe, loophole-free ways of making sure that robots aren't going to take over the world, even without having quantum computers. Because whenever there's a new technology developed, there's always the possibility of using it for good and for bad. So our regular classical computers are a prime example of this. So with new quantum technology, there will be examples of where you can use it for good and for bad.
Yeah. And we haven't achieved artificial general intelligence yet, as far as I'm aware anyway. Do you think quantum computers can help us get there? And
so
should we be trying to achieve that? That's a different question altogether.
Yeah. So artificial general intelligence is very different to just artificial intelligence, because it means that a computer can solve a general set of problems in more like a creative way, like a human can do, instead of just a very specialized specific problem. So I think it does make it more scary because it has more chance to be able to replace humans in particular jobs because they can think more freely and solve a wider range of problems. And I would be very concerned about reaching the so-called singularity, which would be where humans are now no longer smarter than the machines that they have developed. So if we get to the place where artificial intelligence takes off and develops more and more powerful iterations of itself, then we could have the scary concept where it's now more intelligent than humans. And I think we need to have very serious laws in place before this technology reaches that maturity level.
Yeah. All right. So I think that's most of the questions that I wanted to ask. There's so much things that I can just continue talking about this topic for a long time. But I think we've had a good discussion, and I want to go to the closing section of the podcast and just cover off the last few interesting questions. The first one I have is, do you guys believe in the simulation theory and whether or not we're living in a simulation?
Well, I haven't gained any evidence that we are living a simulation yet from my own personal experience. But then again, how would we know? Like, if the simulation is so convincing, then how would we know? But maybe we could find ways to find out if we are living in a simulation. If we could, for example, probe the universe on more and more tiny scales by using more powerful particle accelerators, maybe one day we'll be able to find a glitch in the matrix, for example, that could be caused by computer rounding errors, and it might indicate that we are living in a simulation. And if that's the case, what would I do differently? Like, I think I might still continue researching quantum computing because it's just so interesting.
Yeah. Or just trying to like break the simulation with your quantum computer.
What do you think, Biliana?
I think my partner has tried to bring this, the mathematician, he's tried to bring this up several times. I think my eyes glaze over. I'll leave that to you guys.
Yeah, because I think I'm not like a huge believer in it either, but it's like the phenomenon called deja vu, where you feel like you've experienced it before, and what if you're just living in a simulation and you've already lived this life like multiple times? Yeah, I don't know. It's really hard to say like whether we do or not, and it doesn't really change anything if we do, because you'll just continue to live your life as it is.
Maybe I'd try harder to learn to fly or something, like just try and really appreciate that I'm living in a simulation. So I'm going to just try and jump off a cliff and fly, but that might be dangerous.
Yeah, that might just be a little bit dangerous. The other question I like to ask is, what are your favorite books? Like, do you have any good book recommendations that had a major impact on your life?
I can definitely think of one book that had a major impact on my life in leading me down the path of studying quantum computing. And that would be probably when I was a teenager in high school. I found this book called Quantum, A Guide for the Perplexed by Jim Al-Khalidi. And Jim Al-Khalidi is a famous theoretical physicist who's on lots of documentaries, a bit like Brian Cox. And this book was so fascinating. It told me about the weird and wonderful world of quantum physics and how there's these things called electrons that have spin and they can be spin up and spin down at the same time. And it kind of blew my mind. And it probably subconsciously influenced me to follow down this path of quantum physics and just trying to get real world applications out of this really cool science. So that would be a book that I would recommend you could read if you're interested in getting into quantum physics.
Sure. And what about you, Biliana?
I think the last book, I used to read a lot more sort of 10, 15 years ago, and they used to be more around finance, especially after the GFC. There was one book called Fooling Some of the People All of the Time that was quite insightful and entertaining. But the last book I've read last year actually was Never Split the Difference,
Okay.
from a former FBI hostage negotiator. And I just found that interesting in reading his stories, real life stories that he was in, and then also talking about human behavior and what drives humans to act certain way or act other ways. To me, that was just really interesting. More so reading the situations that he was in.
That's super
That
interesting. I've written that down and I might have to read that book and it might help me get more grant funding if I can really crack the code for how humans think.
Yeah, for
yeah.
me, it wasn't more about being a better negotiator, but it was more about just understanding people.
Hmm. Yeah, what does it mean by the phrase like never split the difference? Like, is there a meaning of that?
Walk away with everything.
Okay, so never compromise, basically.
Never compromise. Yeah, yeah. If if you have $10, walk away with it all. Why split 5-5 and everybody goes home happy? No.
That's a very interesting philosophy. Um, but that's okay. Last question is, do you guys have anything else you want to share with the audience? This could be a plug for something or just a final message you want them to take away.
Final message for me is that quantum computing is extremely cool and rapidly developing. And it's such a fast-paced area to work in, and there's many ways for people from different fields to get involved with it because we're going to need more broad, like engineers, people trained in classical physics and not just like pure quantum physicists to get involved to make this technology work. That I think it's really exciting time to be involved in it. And yeah, I guess if you want to follow what I'm up to, you can follow me on LinkedIn. My name's Danielle Holmes and I work at UNSW in Sydney.
And a final message for me will be, I think, continuing on what Danny mentioned is this is an area that's going to require a lot of different skill sets, and all of those that Danny mentions, but also if you're going to be developing product, user interface designer or user experience designer, somebody, a corporate communicator, a marketer, operations. Like there are many ways to be involved in quantum outside of research, with all these companies that are still coming out of research labs and also those that already are established. This isn't just for those who have masters or PhDs in quantum. This really is touching us all. And so it's really, so if you're considering a career quantum, just because you studied marketing doesn't mean you don't get to work at a quantum company. You absolutely can if you have that curiosity and interest to be there.
Yeah. Well, those are both great messages. And yeah, I think it's definitely a very interesting field. that everyone should give a thought of working in, because I feel like it would be very rewarding. But thank you both for coming on the podcast today. It was really lovely talking to you. And yeah, thank you everyone for listening as well. Bye.
Thank you, Adi, for having us. Bye.